Okay, welcome to DC Circuits for Ncea Level 2. These are two games you can play. This one here, you want to learn, this one here, you want to learn the circuit symbols. This one here allows you to work out where currents go in a circuit when they split at junctions and when they are the same everywhere in series. So just a quick summary, current is the rate of flow of electric charge. Okay, so think of a river. So here's our river, and there's water flowing down the river. Now, water flow can vary in two ways. One, you can make it much faster. Okay, so you can make it speed up, and if you do that, then you increase your rate of flow. But we could also widen the river and make it deeper and get a much larger volume of water passing through a point. Then we could also change the rate of flow. Voltage effectively provides a current. Okay? To create a voltage, what you need to do is first separate some charge. So when you have a charge separation, like this, you have created a voltage. There's a tension. These charges want to head back towards the positive, and the positive want to head back towards the negative. So there's a want to do something. So that is a voltage. They want to do something. It's a potential energy. In this case, if this was a metal ball, they would just flow back, so there would be a current. So this voltage can create a current. Or if we had two separate objects, and this one was positive and this one was negative, and we connected them with a wire, then they could balance up. So what happens would be a current would flow from one to the other. Okay, that's the actual electrons would flow from the negative to the positive. Okay, be aware that's different from actual current flow, which we decide as being from positive to negative, even though the electrons are going the other way. So a voltage essentially is a separation of charge, and that creates a current. There's a difference in energy from one place to the next is the actual measure. So if we think about this ball here, there's a certain amount of energy stored where those things are separated. When they are combined, there is no energy. Okay, no energy stored. So that change in energy is actually the voltage. On an electric circuit, as a current flows through something like a resistor, it might have a certain energy here, and then it'll have an energy afterwards, and that difference in energy from one side to the other side will tell you your voltage. So for example, here's a circuit. Here we have a supply which increases the energy of the charges. Okay, so it actually provides energy to the charge. In this case, 12 volts. So there's 12 joules per coulomb at that point. Now that doesn't change in a wire. It's always 12 joules per coulomb. So as the coulomb flows around the circuit, the amount of energy it actually holds doesn't change until it gets to some resistance that it has to force its way through. So that's when it uses its energy. So as it gets to this 14 ohm resistor, as it gets there, it will lose energy. Okay, and in this case, there's 12 joules on this side, and then as it goes through, it ends up with 5 joules on this side. So it's got a voltage, a change of 7 volts, a potential difference. Okay, so 7 volts is the change, and that's what the voltmeter reads. It's the change in voltage. Now it's got 5 volts here, and as it goes through this 8 ohm resistor, it now has 1 volt or 1 joule for every coulomb. So it's used 4 joules per bit of charge to get through this 8 ohm resistor. And you can see it requires more energy to get through a higher resistance than a lower resistance at the same speed or the same current. So as the current flows through, it then reaches this 2 ohm motor, and as it goes through this one, it loses just 1 joule per coulomb, so it'll be left with none as you come back here. And we usually say that wires require no energy to flow through them, but in reality this is not the case, as you'll see when we do experiments. So something else to do with current, okay, current is the same everywhere in a series circuit, okay, so if we look at this point here, it's the same there, there, the current's always the same. It's like a flow of a river, okay, so imagine that this thing was actually a river, okay, so water's flowing along and it stays inside the river. There's no little junctions heading off, okay, it stays in the river. When you get parallel, the river flows along and then gets to a junction, okay? And what happens there is the river's going to split 3 ways in this case, okay? And usually if there's a small restriction, so in other words a higher resistance, then there'll be less current going in that direction. So if this was, let's say, 2 ohms, so if it was 2 ohms, yes, more current would go this way now. So we have heaps of current this way because it's easier to get through the 2 ohm resistor. Well, less current will go this way and this way because it's harder to get through. So this way is more current. I hope I said more current, might not have. More current this way, less those 2 ways, because the pipe this way is bigger and these are smaller. Okay, so imagine like small rivers, small little streams, and a large river. As the current comes around and hits the junction, most of it's going to go the easier direction. When you talk about resistance, depending on the size of resistance and the amount of push, a certain current will flow. Okay, in other words, we have our push. Okay, the amount of charge separation will then decide the amount of flow. Okay, if we double our push, then we have double the current. Vice versa, if we have the same amount of push in each, but we then double the resistance, we have half the current. In other words, you might have the same amount of push to get through, amount of energy to get through that resistance, but that resistance actually means, if it's higher, that energy means it'll be used up to make less current. Oh, the formulas didn't work. Okay, so first formula here is I equals Q over T, okay, and that's the rate of flow of electric charge, that's your current. Then you got V equals IR, and the last one here, V equals E over Q. This one here is what we just talked about before. If we increase the voltage, we will increase our current. If we keep the voltage the same, and we increase our resistance, then current must decrease to keep voltage the same. When you combine resistors in series, you just add them up. They get worse and worse. So the more resistors you add in series, the more energy you need to get through them. Okay, and if you don't have more energy, then you're going to go slower. In parallel is 1 over R total is equal to 1 over R1 plus 1 over R2, etc. Okay, so let's look at examples. So the first one here is just straightforward. It's just 20 ohm resistor. The second one is we're doubling our resistance because we're adding 2 in series, and that makes 40 ohms. So you add the 2 together. When you have 3 in series, effectively you're just adding 3 in series to get 80 ohms. For when you got parallel, just 20 by itself, when you add another one in parallel, you're actually making the pipe from being this size, or from a smaller size that we had up here, to actually a larger size pipe. So you're doubling the width of the pipe. So we end up with only 10 ohms in this one here, when you look at the example in the notes. This one here, you're making the pipe even wider again. Okay, so it's going to be 1 over 20 plus 1 over 20 plus 1 over 40 to give you 5 over 40, just put in your calculator. Now that's what 1 over R equals, which is very important. We actually want R over 1, okay? So that means we just flip both sides, so it's 50 over 40 over 5, which equals 8 ohms. So the resistance has gone down because the pipe's got bigger. Now this example, first step, we need to, we can't combine all these ones here in parallel yet because there's a series section to it. Okay, so the middle part is in series, we need to add that first. So for the series part, we're going to have 40 plus 40, and that makes 80 ohms. So now this is just one resistor of 80 ohms. Now we've only got 3 resistors in parallel, so we can add all them up. So we do 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that equals 1 over 20 plus 1 over 80 plus 1 over 40. So that's 7 over 80, okay, and we want R, so that's just going to be 80 over 7. So I run about 11.4 ohms. Oops, running out of room, sorry. Now we're going to combine the series. So effectively all this is turned into one resistor of 11.4 ohms, and it's in series with a 20. So resistance total is equal to 11.4 plus 20, which makes 31.4 ohms. Done.